Hi everyone, my name is Elodie Bousbib. I'm currently working at UPNA Lab in Pamplona in Spain, and today I'm presenting Haptixel, encoding data through cutaneous force-based encounter type fingertip haptics. Data can be encoded through various sensory channels. For instance, data physicalization has been widely explored as physical artifact whose geometry encode data and highlights how physical properties enrich the interpretation of quantitative information through static and dynamic physical representation. Let's say we touch it and directly interact with it. Well, we felt this geometry. Through our skin, we felt the texture, the pressure, the force changes. At the fingertip scale, and when we interact with tangibles, the fingertip pulp and its skin deforms and provides a cutaneous feedback to our brain for interpretation. More importantly, we're used to quantify through our touch. We map whether a plate is too hot with temperature or a fruit has passed with this compliance. So now, what if we remove the data physicalization and focus on our sense of touch? Can we encode data through cutaneous force feedback in visualization tasks? In this paper, we're interested in knowing whether cutaneous force can function as a quantitative channel for visualization context, treating force as a univariate value mapping to either reinforce and augment visual perception or to provide a lightweight alternative when attention is limited. To answer this question, we propose Haptixel, a wearable haptic device designed as an accessible platform for studying force-based color cues as haptic pixels in visualization tasks. Haptixel's concept is to encounter the user's fingertip to provide this cutaneous force feedback. Here, for instance, on the gray pixel, Haptixel is actually not touching the user's fingertip. It then encounters it to provide force depending on the pixel's height and color. The red pixel has a higher force than the yellow one. Hardware-wise, Haptixel's design is open source and really simple. It relies on a servo motor, a crank rod mechanism providing a lever actuation, a finger support, and finally a proximity sensor, a force sensor, and a vibration motor. When the servo motor is on, the lever deforms the user's fingertip pulp. Haptixel's design choices open up a three-dimension interaction framework. Similar to visualization tasks, it can be used without visual support over 2D displays in AR or in VR. We designed Haptixel's form factor to be compact to avoid occlusion while working with typical hand tracking systems. Its second dimension is its force levels. We servoed Haptixel in force so we can control the feedback it provides. First, it can stay out of reach without physical contact. When touching the fingertip, Haptixel can provide a simple contact without force and provide the user with a light touch. Finally, it provides low to high forces, either touching or pushing on the user's fingertip. We conducted a G&D study, and we can reach up to 4 levels, and more details are in the paper. The third dimension is the contact type, either a discrete contact like a stroke or a continuous one. A continuous constant contact of a given force would provide an absolute information, while a continuous varying force indicates more relative information such as ascending or descending. What are the opportunities for data visualization? Well, dimensions can be combined to cover a whole set of mid to low level tasks, but supporting them goes through perceptual requirements. Perceptually, users wearing Haptixels should demonstrate a good force discrimination used in discovery tasks, a high accuracy in absolute recognition, for instance, used in information retrieval, a high accuracy in relative recognition used for sorting or comparing, and a low spread within the same data range that can be used for correlation tasks. We conducted a user experiment to demonstrate whether cutaneous force levels can support quantitative distinctions and be retrieved accurately even without visual feedback, substituting visual encoding. We designed a VR pixel art-like application where participants haptically explored physical patterns which they could not visually see. Participants had to replicate them as coarse heat maps on a blank canvas with colors matching the force levels they perceived. Participants felt and drew 4 patterns. The first one only had 1 force level, representing a cross. Here, the participants draws the cross with a yellowish color. To define this color, participants have a calibration cube to refer to. The difference with this cube is that they control its color and height and are providing with its corresponding force. They can therefore match the force they perceive on the canvas to the calibration cube one. In the second levels, we represented triangles with two levels of forces separated by 1.5 Newton. In the third level, a random design was to be found to remove the bias from drawing known shapes. It grouped three levels of forces separated by 1 Newton. Finally, the last levels was circle, which each force separated by 0.6 Newton. We recruited 16 participants and all of them performed the four patterns of 5 to 5 pixel art canvas. We measured the participants' assigned forces. Using the same color heat map, we can see here on the left the pattern to find and on the right what the participants have drawn in average. Same goes for the second level, the third level, and the fourth level. First, we see that thanks to its uncontoured concept, the on-off, so the gray or the colors, are well defined. Regarding global results, considering all the gray cubes, the global absolute error is under 0.2 newtons, and without the gray cubes, it is of 0.34 newton. But now, what I think is interesting, and even though the absolute error is pretty low, we can notice that sometimes the colors aren't reached as per here in level 3, though each color level is still recognized and well discriminated as belonging to the same sublevel. This does mean that relative forces are understood properly and force levels are discriminated. We decided to look into the data spread by analyzing the 95 CI per force level per user to show how participants were confident pixels were associated among one sublevel. Results were between 0.05 Newton and 0.3 Newton. Finally, we performed a one-way repeated measures ANOVA for the last pattern with a 4-force level. There was a high significant effect between all the sublevels, indicating that participants can discriminate at least 4 force levels using Haptixel plus the non-contact one. We also see that the average and median values are really close to the absolute expected values. Qualitatively, participants mentioned they got lazy to go back to the calibration cube all the time and preferred using pressure and force memory to draw the patterns than to go back to the cube. They mentioned how easy it was to rely on relative force perception to draw the patterns. Strategically, they mentioned using the validation phase to detect whether there was a global offset, like an under or overestimation, and reiterate from there. Finally, they were all quite surprised by the amount of forces they received on the fingerpad and weren't expecting it. From the study, we highlight 5 key findings and their implication for data visualization tasks. Participants perceive the difference between force and no force, meaning that participants can freely discover values in visualization tasks, hovering void zones, encountering data points with an associated value. Participants differentiated relative force levels and actually used it as a strategy to retrieve values, meaning that continuous force values can be interpreted as mapping while exploring data. Third, participants retrieved absolute force with a high accuracy, meaning that Haptixel and Cutaneous force feedback is a viable alternative to encode data when visual attention is limited and to complement visual encoding. Participants clustered data points with a low deviation of data, which demonstrates how beyond mapping a force value, Cutaneous force feedback supports more general visualization tasks such as clustering or correlation. We envision a set of use cases for Haptixel and more generally Cutaneous force feedback in visualization contexts. As participants can discover, retrieve, and interpret spatial data, we propose the use case of geographic data visualization, which illustrates how cutaneous forces can convey topography information, forces to height, or to check population density, forces to density. Participants in our study perceived and actually revealed relying heavily on relative and dynamic force changes. These results can be extended to temporal exploration using Haptixel, for instance, in stock market trend following, where it can encode dimensions as derivative, for instance, trends, slopes, or speeds. As a conclusion, we presented Haptixel, and our contribution are a lightweight open-source fingertip haptic device designed as an accessible platform for studying cutaneous force-based color cues and visualization, and empirical results demonstrating how cutaneous force feedback can support simple quantitative distinction and encode data, enabling users to reproduce coarse scallop patterns without visual feedback. You can find more information in the paper, and Haptixel's design and script are available on my website. Thank you for your attention.